Titanium chloride is a violet color solid, right? So here we have titanium 3 plus, right? So titanium, if you remember, scandium titanium is 4s2 3d2, right? So this is for titanium, but for titanium 3 plus, so this should be 4s0 and 3d1. So you have a titanium compound which is 3d1. So they say this is a violet color solid in water. Two hydrated species of titanium chloride is formed. Okay, A and B are formed. A and B are coordination compounds of titanium with octahedral geometry. So this is very nice because around titanium in the coordination sphere, there should be 6 ligands, right? And these ligands can be either water or chlorine. So this makes our lives a little bit even easier, right? So A and B were separated and their atomic compositions were determined. And there are 2 analyses they have carried out for A and B separately. So write the electronic configuration of titanium in A and B. So you see here, this is titanium chloride, right? So when you have titanium chloride, this is titanium 3 plus. And in the complex, you will have chlorine as one of the ligands, and then water as the other ligand. Since water is a neutral ligand, right? Neutral ligand, here in this particular case, this oxidation state of this titanium is only depending upon chlorine, right? So this is already given here as titanium chloride. So this is just can be changed like titanium Cl1, water something, Cl, let's say water 4. And you know this is +3 from titanium chloride. So this is +3 means -2. So it is going to give +1 for an example because water is neutral. So in the complexes A and in the B, this +3 is not going to change, right? So this will be the same electronic configuration. You cannot write like this. You have to write 1s2, 2s2, 2p6, 3s2, 3p6, like that. Okay. So this is easy. Reduce the structures of A and B. Give the IUPAC names of A and B. Okay. So to again avoid time consuming, I have written down this piece of information in the board so you can see this. So titanium chloride, white color solid. So octahedral geometry, ligands can be only these two, A and B. So for A, they have added AgNO3 to a solution of this of A, and they have obtained. So you know when you add AgNO3, so this complex, one of these two complex will have Cl minus as the counter ion, that is outer from the coordination sphere. Don't forget, outer from the coordination sphere, right? So what you have to understand here then, when you add Ag plus from this outer counter ion, there will be Cl minus and AgCl is precipitated out, right? So how do you find the structure of these A and B? So you have to understand here, we already know titanium here is +3, right? So this is titanium +3. And this +3 with the rest of the ligands is going to determine the amount of counter ion as Cl minus in both these, because try to understand these Cl minus which are outer as the counter ion is going to give these two precipitates, because these ligands inside this parenthesis won't participate for precipitation. only this. Now we have to find how many chlorines here and how many chlorines in A and how many chlorines in B. Chlorides, in fact, in the outer sphere, right? So we have to find that. So how do you find that? The simplest way to get that here, think about this idea. How many moles of AgCl is formed? You can find that. And this number of moles should be equal to the number of moles of chloride that is present in this complex, right? This is one thing. So if you divide this by the molecular weight of AgCl, which is, I think it is 135.5 something, if I can remember, and you will get 0.03 moles here as well as here, right? So you see the amount of moles given by this complex is same, this complex is same, AgCl. But don't forget, the amount of moles here from this A is 0.2 into 50 into 10 to the power minus 3, which is 0.01 moles. Complex moles, okay? And here it is 50 into 10 to the power minus 3 is 0.015 moles. Right? So this gives you the idea. This is the number of moles of complex, like this entire complex. And when you dissolve this complex, 3 times chlorines are given, which gives you the idea for this particular thing. When you have this titanium complex, there should be 3 chlorines outside, because the stoichiometric ratio is 0.01 to 0.03 means 1:3. So from one complex, 3 moles of chlorides are given. And here from one complex, 0.015 into 2 is 0.03. So this is like 1:2, right? So here in this complex, it should be 2 chlorines outside. That is the first point. And the second point is, we have already saw this before, this oxidation state cannot be changed. So if this is 3 chlorines outside as the counter ion, what should be the charge of this positive ion? It should be +3. And in the similar way, if this is 2 chlorines, here the charge should be +2. That is why this becomes neutral then. That is why +2 -2 cancel out, +3 -3 cancel out. So this positive species, the charge is +3, and we know the titanium, the oxidation state is +3, right? So there should not be any negatively charged Cl- here in this species within this inner coordination sphere, right? Because if you have any chlorine in the inner coordination sphere, then +3, for an example, let's say there is a chlorine here, so +3 -1, so it should be +2, so it cannot happen. So the oxidation state of titanium +3 and the complex positively charged species charge is same, +3 +3. So the only possibility to add here is the neutral ligand, which is water. So this one should be titanium H2O6, because the geometry is octahedral as given, right? But here you can see the charge is +2, which gives you the idea, if this is +3, then there should be 1 chlorine here in the complex, right, within the inner coordination sphere, along with 5 water molecules, right? So for here, you have to be like chlorine and 5 H2O molecules. This is chlorine, right? So this is the way that you can predict the structures of these two. And then you can write down the IUPAC name, then this becomes very simple: hexa aqua titanium space, then chloride, and this one pentaaqua, then there is chlorido, then titanium space, then, but don't forget to mention the oxidation state at the end of the positive one. Okay, so this is the simplest explanation that I can give you here. Okay, so this is done, deduce the structures. So you see here, you have to understand that the number of moles of the complex and the stoichiometric ratio of the precipitate form. And IUPAC nomenclature is very easy, right? Right, part 2 of this is X, Y, Z are coordination compounds of the metal ion M2. So here you see the oxidation state of this is +2. They have a square planar geometry. Okay, so all these X, Y, Z, they all have square planar geometry. So which means M should be like this and 4 ligands should be combined like this. X is a neutral compound, right? So we have given X. We can clarify no charge, and it's a square planar compound. Square planar, no charge. This is X. On addition of barium chloride to an aqueous solution of Y, okay, a white precipitate that is insoluble in water. So basically this is talking about barium sulfate, right? So in Y, one of the counter ions that is present or one of the ligands that is present should be sulfate, right? Because Y should contain a sulfate, otherwise this precipitation cannot happen, right? So don't forget about that. So there should be sulfate, and don't forget this sulfate should be in the outer sphere, as we discussed just before, like the chlorides. It should be in the outer sphere. And Z gives 3 ions in aqueous solution. So Z is also the, now this is also square planar, don't forget. Because all are square planar, this is also square planar. And Z gives 3 ions in aqueous solution. Write the structural formula of XYZ selecting the appropriate species. So first thing is you should have 4 ligand at each case. And in this case, in the outer sphere, there should be sulfate. So for an example, if I come from this Y here, this should be M. So the charge is 2 plus. Since sulfate is 2 minus, so there should be a neutral ligand like MHN. NH3 4 times, and here now the overall charge is +2 because M is +2, and there is this counter ion sulfate, and this is Y, and you see this is square planar, 4 ligands in the inner sphere. And they say the first one X is with no charge. So no charge means the charge of the metal ion is +2, which should give you the idea. So the ligands within this parenthesis should have a -2. So we have to select -2. So, but you can't use sulfate because the structure should be like square planar, right? So square planar means if you have 1 M, and if you have 2 ammonia and 2 cyanide, the overall charge is 0 and it is okay. But if you use sulfate, you have already used like 2 and you are going to combine the rest with ammonia, right? So you can do that one as well. But the suitable is like you have cyanide, then cyanide, and then ammonia, right? So now this one will have no charge because this is +2 -1 -1 -2 +2 -2 overall charge is done. So you can write this one as M2 NH3 twice. So xy is done, then finally ez. So ez tells that it will give 3 ions to the solution, right? So basically 3 ions means one can be within the parentheses, that is can be 1 giving some charge, and 2 can be in the outside. So for an example now, but don't forget, still this is square planar, right? So if I think like if I am trying to draw this only with cyanides, so MCN4, what is the overall charge here? M is +2, cyanide is -1 times 4 is -4. So +2 minus 4 is -2. Now this overall charge is -2. So to counter this -2, I can have 2 potassium. So this can be K2, because this will give 2K plus ions, which are 2 ions, and the rest ion is MCN4, 2 minus. So this is 1, this is 2, and total 3 ions, right? So this is not the only combination. You can have many other combinations as well. Okay, so don't forget about that. You can even use ammonia also. For an example, if you use ammonia, so this will give NH3 4 times because it's square planar. So this will have 2 plus. So instead of 2 plus, you can have 2 cyanides outside as the counter ion, right? So when you dissolve this, you will have 1 ion from this complex and 2 ions from this cyanide. So 2 cyanides, so Cn minus, so 3 ions. So this is another possibility. So you can have such possibilities. Right, so we have to move on to the final, question. So I'll share it again. Share it again. So this is part B, electrochemistry. Electrochemical cell is given, right? So one should be anode and the other one should be a cathode here. So following data is also given. So based on the data, so you can see here there's a silver and silver chloride solid. So it is like the standard silver chloride electrode, right? And this one is like mercury with the Ag2Cl2 and Ag liquid. So this is like the calomel electrode, so that is going to be combined. So this is like silver electrode is going to combine with the calomel electrode. Okay, it seems like that, right? But you can see there is no slot bridge or anything, right? So we will try to figure out what is anode and cathode here. So you see here this 0.22 is lower than 0.27, so this should be anode. So our silver is anode here, right? And the cathode is this one, right? Very simple, right? And write down the reduction half reaction of the Bauer cell. So the reduction half reaction means this is our cathode now. So basically what is happening here, Ag2Cl2 solid. So here we have Ag22 plus. So it will take 2 electrons, right? So it will take 2 electrons and it will form Ag liquid, which is in the liquid state, plus, and this Cl minus is removed, right? So 2Cl minus aqueous. So this is our reduction reaction. Make sure you put all the physical state for physical chemistry questions. Write down the oxidation half reaction. So the oxidation is going to happen with silver, right? So silver, which is my solid, is going to oxidize to form Ag plus, but don't forget there is Cl minus, so this is going to form AgCl solid. So there should be Cl minus aqueous here as well. Okay, so don't forget about that. And So this is oxidation, so an electron is removed. So construct the cell reaction. So in the cell, what you have to make the cell reaction. So you have to multiply this second reaction first by 2. So you will get 2 AgCl, 2 Cl minus, 2 Ag, and you have to combine these two. So when you combine these two, so you will have 2 Ag solid and plus Ag2Cl2 solid. So the electron is going to cancel, and in fact chlorine are also going to cancel. And finally you will have Ag liquid and 2 AgCl. So this is the overall reaction, right? So these are done. So you can find the EMF. So it will be 0.27 volt minus 0.22. So you have to write down E cell is E cathode minus E anode, and E cathode is 0.27 volt minus 0.22, which will give 0.05. Give the standard cell notation of the above electrochemical cell. So this is also very simple. First, you have to show the oxidation. So it will be very easy to show the cell reaction, because in the cell reaction there should be silver solid and silver chloride solid, and there should be a phase change giving Cl minus, but you have to mention the concentration and physical state of Cl minus also. Okay, so don't forget. So basically it will be like silver, which is going to oxidize, and it will give silver chloride. You see in the oxidation reaction. So silver chloride solid. So this is also solid. This is also solid. So you don't have to put a phase change here. You just need to put a comma. And then you have the phase change, which will give Cl minus. So in the bracket, you have to put aqueous, comma, and 1 MoLDM minus 3. That is how we usually indicate. And then the reduction. So since there is no salt bridge, we are not showing the salt bridge here. So in the reduction reaction, so Ag2Cl2 solid, and then you can either, now this is solid, then the phase change is Ag liquid, and finally you can show this platinum as well. Okay, at the end. This is very simple. And the next question, 6. Does the electromotive force of the above electrochemical cell depend on the chloride ion concentration? So the only thing that you have to check here is, here is also chlorine involved. Here is also chlorine involved in the oxidation and the reduction reaction. But to check whether this depends upon the electrochemical cell electromotive force, you have to check the overall cell reaction. So you see here in the cell reaction, Cl minus is not involved. So you can give it a direct answer. The electromotive force does not depend on chloride concentration because it is not involved in the overall cell reaction. Okay. Calculates the change in mass of Ag solid plus Ag solid, Ag plus Ag solid, AgCl solid when a current of 0.1 was drawn for a period of 60 minutes from the cell. So basically you can calculate the charge from this two, because we know Q is equal to IT. So here the ampere is 0.1 and time is 60 minutes, which is 60 into 60, because we have to calculate in coulomb, so we have to convert that into seconds. So this is like 16 to 60 is 360 coulombs, capital C, coulombs. But this is the charge, but we have to calculate the moles. Okay, charge number moles. So which is equal to the electron moles. So you can calculate the Okay, I will write down like this, electron moles. So you can use the Faraday's constant. So it will be 360 coulomb divided by 96,500, right? Coulomb per mole. So you can get the electron moles from this calculation, 96,500. So you divide this and find the number of moles of the electron, right? And finally, you have to understand one point, what is actually happening here. Here you have silver, and silver get oxidized to silver plus. So think about that. So silver get oxidized to silver plus, and one electron is removed in this particular reaction. And we have found this electron number mole from this equation. Because what is the remaining process? The remaining process is 1 Cl minus from this solution is going to combine and form AgCl. So principally, the electron mole is coming from this electron, because when silver plus is formed, automatically it will combine with Cl minus and form AgCl, right? So the electron ratio and this ratio is 1:1, like, right? Because silver get oxidized to silver plus and one electron is removed. So the stoichiometry is 1:1 here. And this one Ag plus is going to combine with one Cl minus to form AgCl. So the electron moles formed here is same as the AgCl moles that is going to precipitate out, which is the sum of Ag and Ag solid, the final, right? So what you can do here is you can tell the one Ag plus is going to combine with one Cl minus to form AgCl, right? So here Ag is converted to Ag plus. So it's like the mass is going to reduce a bit, but don't forget this Ag plus again combined with Cl minus to form AgCl. Okay, so finally it's like Ag is converted to AgCl. That is what they are asking. Ag solid is converted to AgCl. So the final mass is like the additional mass of AgCl that is formed. So this is the same, the stoichiometry is same. So the mass of this is 360, then 96,500. So you now know the number of moles of now AgCl as well, which is equal to this. Then you just need to multiply it by the molecular weight of AgCl. Okay, so this becomes very straightforward. But don't forget, when you are multiplying, you have to multiply by considering what is actually increasing, right? So here is also Ag and here is also Ag. So what is the additional amount? The additional amount is chlorine. Otherwise, you have to multiply by AgCl, and again, you have to reduce this Ag plus again to get the additional amount, because they are asking Ag solid plus AgCl solid. So Ag is converted to Ag plus means Ag atom is missing. And this Ag plus combined with Cl minus to form AgCl means again the missed Ag is formed, but additionally there is chlorine. So the real weight is like the amount of electrons here formed here times 35.5 gram per mole, which is only the mass of Cl minus. So you will get the mass here. Otherwise, what you have to do here is from here, what you have to do here is you have to show that separately, like 360 over 96,500 and AgCl, which is 108, I guess. AgCl is 108, yeah. 108, 35.5 minus 108. So you see these two cancel out, that is why it is. Okay, so the increment of weight here comes basically from additional Cl minus, because CS Ag is solid is converted to Ag plus, so Ag is missing, but this Ag plus combined with Cl minus to form AgCl, so again the missed Ag is formed, but additionally you have chlorine, so that is why here it is 35.5. Right, so that is also done. So finally, what would be the chloride ion concentration in the solution after drawing the current into above? So you have to understand here, right? This setup is done using this amount KCl 1 MoLDM minus 3. So basically, we add this KCl to maintain a constant chloride ion concentration. That is our main objective here. Okay. So when you draw this current, automatically you think, okay, some amount of chlorine is now taken here according to this one, right? Because Cl minus is combined with Ag plus to form AgCl. However, don't forget there is this reduction reaction that is happening here, right? Forming chloride again, right? So basically at the end of this reaction, or maybe after the end of this current, after for 60 minutes, the chloride ion concentration does not change. That's the idea. It will not change. Right, so that summarizes our comprehensive discussion of these question number 8, 9, and 10. Okay, so we'll see you next time in 2018 MCQ. So take care all.